Hey guys, welcome back to our flipped video lessons. It's been a little while, but we're back here to talk about what happens when we take linear functions and we compare them on the same coordinate plane and to understand the relationships that they have with each other, right? So we've talked a lot about linear equations and linear functions in this unit here. In Target 4, we talked about what a solution was and how do we represent an infinite number of solutions. In Target 8, we talked about how to graph those solutions if we're given an equation in one of our four forms: slope, intercept, point, slope, vertical, or horizontal form. And in our Target 7, we talked about how to write those equations in those forms if we are given information about the solutions. Right? We also learned about inequalities, and we learned what does fx say. That's right. You all know right now in your head, you're thinking exactly what you know you're thinking there. So just enjoy that, and remember, it will never leave you for the rest of your life, even on your deathbed. And again, this pops up. Don't show this message again. On your deathbed, you'll be thinking, why, right? So, but anyways, what we're here today to talk about is what happens if we take two linear equations or linear functions and we graph them on the same, graph the solutions on the same coordinate plane, right? Well, essentially, there's only two things that can happen if we graph them, the solutions, on the same coordinate plane. The lines that we get of the solutions can either intersect or not intersect, right? They can be intersecting or be non-intersecting. Pretty straightforward there. There's really the only two options on a two-dimensional coordinate plane. So if we break these two relationships down, or these two categories down, there's kind of three different specific relationships that the graphs of our solutions can have. They can have a single intersection, right? Just like we can see here, these two streets, they will intersect once and then never intersect again in all of the infinite number of ordered pairs that are on those lines. They could be coinciding, right? Coinciding, we've talked about this, I think, before, but coinciding means that two graphs are literally right on top of each other. They're literally the same line. You can see the example down there. There's times where we have highways, we have roads, where two roads will merge together for a period of time. And even though it's one road, it is considered two different names there. You can see we have Tollway 17 and Highway 60 are the same road there. This happens for us for 83 and 60, Route 83 and Route 60. For those of you who don't drive yet, you probably don't know where that is. But those two roads come together and coincide for a period of time. The third relationship is that two lines can be parallel, right? And we can see here our two opposite lanes of traffic should always be parallel. They should never intersect each other. So what we're going to do in these notes is we're going to take a look at these three relationships and examine what is it about our equations, what is it about the slope, what is it about the ordered pairs that cause these relationships to happen. So let's start off with our intersecting lines. So first of all, I want you to take a second, pause the video, and I want you to find the slope of the black line and the slope of the red line. Ready? Pause. All right, let's see what you got here. Did you find the slope of the black line was 10/3 and the slope of the red line was 5/6? Hopefully you did. You could count up 10 and right 3 and up 5 and right 6 there. So what we should see here is that these two lines, their slopes are different. And this is the important fact we've got to remember when we're trying to decide if two lines will have a single intersection. They will have a single intersection if the slopes are different, right? Okay, so let's talk about coinciding, right? These are our two roads that are actually the same road, right? So notice we have an orange dashed line or a yellow line, sorry, and then a green line there. So take a second again. What is the slope of the green line and what is the slope of the yellow line? Ready? Pause. All right, hopefully you decided. They both have the same slope of -1/3. If you go down into the right, it'll actually be down 2 and right 6, which simplifies to 1/3. Since they're going, the graph is going down from right to left, we know that slope is negative. So if the slopes are the same, that isn't very distinguishing for us. So let's look at the y-intercepts. So I want you to take a second, again, pause the video, and what are the y-intercepts of each of these lines. Ready? Pause. All right. Hopefully, you recognize that not only are the slopes exactly the same, but the y-intercepts are exactly the same. Right? So we can see here that if our solutions are going to coincide, the slope and the y-intercept of our equations have to be exactly the same. Now, why is this important? Well, because when we get to our non-intersecting lines, which for right now in our two-dimensional purposes means parallel, right? Again, let's look at the slope here. What is the slope of the maroon line and what's the slope of the purple line? Ready, go. What you should have noticed here, guys, is that the slope of these lines is the same as well. So this tells us that just knowing the slopes are the same is not enough information to distinguish whether two lines are coinciding or whether two lines are going to be parallel. But what are the y-intercepts of each of these lines? Well, on the maroon line, we can see that our y-intercept is around 0, 1.5. Our purple line has a y-intercept of 0, -10. So our lines are parallel when the slopes are the same, but the y-intercepts are different. Now, hopefully we've been able to notice here that everything that we've been working with to distinguish the solutions as single intersection, coinciding, or parallel does depend on the slope and a y-intercept, right? So that means what form are we going to need our equations in to be able to distinguish these relationships? And hopefully you understand and remember that that means we need them in slope-intercept form. Point-slope form will not be a specific enough form to distinguish the relationships of the solutions of our equations or functions. We've got to have them in slope-intercept form. All right, so let's take everything we just talked about and sum it up into one table here. So we have everything in one nice, neat place to go back and refresh our memory from. So if we have a single intersection and our lines are in slope-intercept form, the slopes are different, right? That's our clue to tell us we have a single intersection. For coinciding, the slopes and the y-intercepts of our equations, of the solutions, will be the same. And if the lines are going to be parallel, the slopes are going to be the same, but the y-intercepts are going to be different, right? So there we go. That's all the information we need to be able to distinguish what relationships our equations or functions will have if we have our equations or functions written in slope-intercept form. So let's actually do this stuff together here. So we've got four pairs of functions here, and we need to determine whether these lines are parallel, have a single intersection, or will be coinciding. So if we look at our first example, the first thing we should look at is the slope. The slope of f of x is -3. The slope of g of x is 5. Those are different, so that's a single intersection. In 2, the slope of f of x is -2. The slope of g of x is 1/2. That's different, so single intersection there, right? So in 3, we can see the slope of f of x and g of x is both 3/4. So now we need to move to the y-intercepts, because if the slopes are the same, it could be coinciding or it could be parallel. We don't know, right? So we look at the y-intercepts. The y-intercept of f of x is 0, -1. The y-intercept of g of x is 0, 8. That is different, which means these lines are parallel. In our last example there, our slopes are both 4. Our y-intercepts are both 0, 3, which means these solutions of these functions would be coinciding. All right? Hopefully this makes sense to you. So let's give it a try now on your own. One warning that I will give you when you're working on these, but also working on problems in the notes and in the homework and in the future, make sure that all of your values, all of your coefficients and all of your constants and all of your factors in your equations are fully simplified before you make a decision on whether the slopes and the y-intercepts are the same or different. All right? So go ahead. You have 8 pairs of functions here. Go ahead and decide whether these functions are parallel, have a single intersection, or are coinciding. Ready? Pause the video now. All right. Let's see how you did. Hopefully you got parallel, single intersection, coinciding, single intersection, parallel, coinciding, and single intersection. right? If any of these were confusing to you, if you're unsure on why these relationships are what they are, please make sure you make a note of that and bring your questions to class, and we will talk about it tomorrow. Well, that brings us to the end. I know, it's sad. You really wish these flipped video lessons could just keep going on forever, all three of you out there. For the rest of you, we'll see you in class.